The last time we were speaking to each other, I left you off at these examples, and we need to work through these together to see how well that you did as far as your product formation goes. So for part A, it gives me an alkyne, and it says, what would happen if you added H2 and palladium to it? Well, it completely destroys that double bond, triple bond. It destroys them all. All right, so 1, 2, 3, 4, 5, 6. All right, there's 6 carbons in total. I know that it's going to completely destroy the triple to a double, the double to a single. So 1, 2, 3, 4, 5, 6. There you go. That's all there is to it. If I want to draw it out skeletal, 1, 2, 3, 4, 5, 6. Hexene. That's going to be the structure. Next one, B. B says H2 Linlar. All right, so for this one, I know 1, 2, 3, 4, 5, 6. All right, so I'm going to draw 6 carbons in a row. 1, 2, 3, 4, 5, 6. On carbon 2, that was a triple bond. That triple bond is going to be broken to a double, and hydrogen is going to be added on. But hydrogen is going to be added on to the same side. I don't know if that's what they want or not, but just in case, I'm going to show it because Linlar catalyst gives me cis every single time that they happen. So I'm going to redraw this, and I'm going to do carbon, carbon. There's my double bonded area. And I'm going to show a hydrogen pointed up and a hydrogen pointed up. So they're on the same side. I could draw them both on the bottom if that's what I wanted to. No big deal. I've got a carbon that's here, and then down below, I've got a 1, 2, 3 propyl group. If I want it to clearly show the cis formation, that's how I can do it. Skeletal structure, no difference. Normally what happens here is that I'll do a double bond like this, and two sites. Hydrogens we will draw to clearly show they're on the same side. That represents 1 carbon already. Here's the 1 carbon for the propyl group. There's the 2nd carbon for the propyl group. There's the 3rd carbon for the propyl group. You pick your evil, whichever one you like. They all mean the same thing. Okay, so for C, I get this triple bond molecule again. 1, 2, 3, 4, 5, and 6. And this time they're adding sodium with liquid ammonia at -78. Okay, so I do this just as before. 1, 2, 3, 4, 5, 6. The triple bond was right there. I'm going to break the triple to a double. 2 sites of attachment open up. There. This allows trans to go on, so I can stop there and say, here's your product. Hopefully you'll be okay with that. If you're not, and they want to draw it another way, perfectly fine. Carbon, double bond, carbon, and I draw the feet. That's what we've seen before in the past. The hydrogens are on opposite sides, so there's my trans. And this left-hand carbon, it's got a methyl group, so I draw a carbon there. And then on the right-hand side, it's got this propyl group again, so there we go. If you're not happy with that, there's another way that we can draw this sucker. 1, 2, my double bond. There's 3, 4, 5, and 6. And here I'll put hydrogen up, and there I'll put hydrogen down. Okay, folks, there's A, B, and C taken care of in less than 4 minutes. Again, we're on a row. Nothing new. Nothing new. So I'm going to get rid of this. That way I can make myself some room. And now we go to D. D has this alkyne. I'm just going to redraw it. 1, triple bond, 2. Then that goes to a carbon. Points up, it goes to a carbon. Points up, that goes to a carbon, and then down to a carbon. That's what we've got. And we're adding this borane stuff. Borane, THF, OH, H2O, 2H2O. Anti-Makovnikov right there. Anti-Makovnikov. It goes on backward. Hydrogen's going to come in and it's going to go, I'm not going to play with you. I'm going to go to the other side. Okay, well, let's figure out what side it goes to. The carbon to the left has a hydrogen. The carbon to the right doesn't have one. There's 4 bonds there. So the hydrogen's going to come in, and normally it would go left-handed, but not in this case. Boing! It's going to go here. So my triple bond breaks, and that breaks to a double. 2 sites of attachment open up. I've just added the hydrogen where it needed to go, and my OH will get added on there. Well, this is an enol, so let's clean it up. I'm going to take this hydrogen that I've added, get rid of it. We understand it's there. I'm going to take my double bond, break it. That gets shifted inward to make my C double bond O. There you go. There's your structure, and that's called an aldehyde. Don't know how to name the aldehyde, but it's an aldehyde group. Let's look at E. Let's do the same thing. Carbon. That goes to a carbon that's involved in a triple bond, and I have a carbon there. Then I have another carbon, and another carbon, and another carbon. Double check yourself. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is another borane addition. That borane addition is going to add on my OH backward. It's going to look at the carbon to the left. There's no hydrogen. It looks at the carbon to the right. There's no hydrogen. It doesn't really matter where this hydrogen is going to go. So, triple bond breaks to a double. 2 sites of attachment open up. Let's just randomly put hydrogen here and my OH group there. That's an enol. It rearranges. I'll clean this up. And my C double bond O forms. Well, that's one product. That's not your only choice, though. Because I could have 1, 2, 3, 4, 5, 6. Here at carbon number 2, I had the triple bond. I could have done this. Triple bond breaks to a double. 2 sites of attachment open up. I could have put hydrogen to the right, and my OH group would have went there. Remember, there's no difference in those carbons. If that happens, rearrangement still goes on. I'll erase those, and I'll form my C double bond O on the second carbon, not the third. Both of these folks will actually form. For part F, let's look at that one. For part F, I'm going to get 1, 2, 3, 4, 5, 6 again. Okay, so 1, 2, 3, 4, 5, 6. On carbon 2 is where my triple bond is at. And this time I'm adding water acid. So this goes on like normal. All right, so the hydrogen's going to come in, and it's going to look at these 2 carbons, and it's going to play with the one that has the most hydrogens. But folks, we've already discussed this. The carbon to the left has no hydrogen. The carbon to the right has no hydrogen. So it really doesn't matter where this hydrogen goes. Either one's going to be okay with it. So the triple bond will break, and that opens up 2 sites of attachment. Let's just put hydrogen here and OH group there. There's my H and OH from the water. Well, this is an enol. The enol rearranges. I know this already. So my double bond goes to a single, and then my carbon to oxygen forms a double bond. Folks, these 2 are identical. Remember, I told you that they are. For the most of the time, they are. And what do you think my other product's going to be? That was one choice. My other product is going to be this one here on the end. I could have put my OH group to the left, not the right, and enol still would have rearranged, and it would have given me that C double bond O on that second carbon. That's how we do it, folks. Now, I know that drawing these structures might look a little different than what you see in textbooks, than what you see on Google, or whatever kind of search engine that you want to use. So I don't really ever want you to forget that there are proper orientations for these things. And folks, this is what you would see as far as answers go, maybe in Blackboard or a standardized test or some type of an assignment that is done by computerized models, some type of drawing software. So for part A, here is your hexane, or hexane, sorry, there's your hexane, drawn normally zigzaggedy. For part B, here is your molecule that is drawn in the cis formation. They don't even write the hydrogens up here at the top. They just leave those off. But they make it so that it curves around to give you the illusion that cis is there. For C, this is the trans orientation. And again, the trans orientation is normal, and that's what creates this zigzaggy line. And once more, that would be pointed up, and this would be pointed down. So they leave those hydrogens off. They don't even write them. It's understood to be that way. For D, well, this is the only way that we can get an OH group on the end, and this is a way that they would represent that without drawing carbons and hydrogens for the most part. There's your true skeletal structure of that aldehyde. For E, we said there were two products that formed, the C double bond O on the second carbon and the C double bond O on the third carbon. Again, skeletal structures, very minimal written down, except the double bond O, which is pretty important in those structures. For F, same thing. No difference. It gives you the same products, just like before. Okay, so there's you some examples to take home, to study, to prep, to look at when you answer those Blackboard questions, but hopefully not to look at when you do my test. That's a different story. So in the next video, we're going to pick up from here, and we're going to focus on a different aspect of these reactions. We're going to talk a little bit about acid and base chemistry again, just because we can. We're at a point where we can do this, where it kind of meets hand in hand in the world of alkynes, and we can begin to relate this in a different way, and we can bring in a different type of reaction because of that. So with that said, stay tuned. We're getting ready to go on another venture together, and that adventure is going to be acid-base for alkynes.